Hello everyone, welcome to the course Signals and System. In this lecture, let us explore the fundamental concepts of convolution integral. To begin with, let us recall what is an LTI system. An LTI system is a system which satisfies both the linearity and the time invariance property. An LTI system is completely characterized by its impulse response. As you all know, impulse response is the response of the system to a unit impulse signal as the input signal. So, given the impulse response of a system, the output of the system can be determined for any arbitrary input signal. Thus, the response of the system is nothing but the weighted sum of the shifted impulse responses. This weighted sum of the shifted impulse response is called as the convolution integral. In this lecture, let us explore the step-by-step process of computing the convolution integral. The convolution integral is mathematically represented as x of t convolution h of t. This denotes the symbol of the convolution. Mathematically, it is expressed as y of t is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau. Thus, output is expressed as the weighted sum of shifted impulses, impulse response. The convolution can be calculated in 4 steps. The first step involves the time reversal process, otherwise called as the flipping. In this step, we compute the time reversed signal of the unit impulse response, that is the h of tau. Next, the time reversed signal is shifted. Hence, we obtain the signal h of t minus tau. Thus, the time reversed signal is shifted by t time units. Next, the time shifted signal is multiplied by the weight x of tau. So, we obtain the product x of tau into h of t minus tau. The last step, the product x of tau into h of t minus tau is integrated over the interval minus infinity to plus infinity, which gives us the final output y of t. So let us explore this steps with an example. So let us consider the example of finding the convolution of x of t and h of t, where x of t is defined as t from the interval 0 to 1 and 2 minus t from the interval 1 to 2. And the impulse response of the system is defined as 1 for the interval 0 to 2. So to solve this problem step by step, the first step is to redraw the signals x of t and h of t on the tau axis. Hence, we obtain x of tau as tau for 0 to 1 and 2 minus tau for 1 to 2. And we obtain h of tau as 1 for 0 to 2 on the tau axis. Next, we find the time reversed version of the signal h of tau. Thus, we get h of minus tau. And then this time reverse signal is shifted in time by t units. Thus, we get h of t minus tau as 1 from t minus 2 to t on the tau axis. Now, we time shift the signal h of t minus tau for each value of t, and then we find the product x of tau into h of t minus tau for every value of t. So now we will consider the different cases of t. So first let us take t less than 0. So when t is less than 0, the h of t minus tau signal lies in this region, and for when we vary the value of t from minus infinity, the product is 0. That is, the signal h of t minus tau and x of tau does not overlap with each other, hence the product is 0. Thus, we express x of tau into h of t minus tau as 0 for all values of t. So, this definition holds until the value of t reaches 0. Next, when we further increase the value of t from 0, here we see that the signal h of t minus tau and x of tau has a overlapping region. So therefore we have some product value for x of tau into h of t minus tau. So in this region, the h of t minus tau takes the value 1 and x of tau takes the value tau. So therefore the product is 1 into tau. So this value exists for the values of tau from 0 to t. For remaining other values, it becomes 0. Hence we express the product x of tau into h of t minus tau as tau for 0 less than tau less than t, and it is 0 elsewhere. So this definition holds for the value of t ranging from 0 to 1. Okay. But further, when we increase the value of t from 1, the definition changes. Here, if we can observe that the product is tau 1 into tau for tau values ranging from 0 to 1, and beyond 1, if we see here, the product is 1 into 2 minus tau for 1 to t. Hence, we write x of tau into h of t minus tau as tau from 0 to 1, and it is 2 minus tau from 1 to t. So, this definition holds until the value of t reaches 2. Okay. So, when the value of t reaches 2, the product, after when we further increase the value of t from 2, the product changes. So, when we further increase the value of t from 2, we can observe that the definition of x of tau into h of t minus tau changes to 1 into tau from the value of tau from t minus 2 to 1. And further, if we go beyond 1, the product becomes 1 into 2 minus tau. So therefore, we write the product as x of tau into h of t minus tau as tau for t minus 2 to 1 and 2 minus tau for tau ranging from 1 to 2. Okay, and it is 0 elsewhere. So this definition holds until the value of t minus 2 reaches 1, that is t equal to 3. Okay, so therefore for x of tau into h of t minus tau is equal to tau for 0 t minus 2 to 1, and it is 2 minus tau from 1 to 2 when value of t ranges from 2 to 3. And further, if we go beyond 3, t equal to 3, further the definition changes. Here if we see, the value of the product is 0 from 0 to t minus 2, and it is sorry t minus 2, and it is equal to 2 minus tau from t minus 2 to 2. So therefore we can say that x of tau is equal to h of t minus tau for is equal to 0 for 0 to t minus 2, and it is 2 minus tau from t minus 2 to 2. Okay, so this definition holds until the value t minus 2 is equal to 2, that is t is equal to 4. When we further increase the value of t from 4, the signal x of tau and h of t minus tau does not overlap with each other. Therefore, the product is 0 for all values of tau when t is greater than 4. So with this, we stop varying the value of t, and then we integrate the product x of tau into h of t minus tau for the various values of t. So let us now consolidate the product x of tau into h of t minus tau. So it is 0 for all values of tau for t less than 0, and it is equal to tau from 0 less than tau less than t for t ranging from 0 to 1. And when t ranges from 1 to 2, the definition becomes tau is equal to 0 to 1, 2 minus tau for 1 to t. And then for t ranging from 2 to 3, the definition becomes tau for t minus 2 to 1, and it is 2 minus tau for 1 to 2. And when t ranges from 3 to 4, the definition becomes 2 minus tau for t minus 2 to t, and it is 0 for all values of tau for t greater than or equal to 4. Now for each range of t, we have to integrate and find the value of y of t. Thus we calculate y of t using the equation integral minus infinity to plus infinity x of tau h of t minus tau d tau. For 0 less than t less than 1, y of t is equal to integral 0 to t tau d tau. So when we integrate and substitute the limits, we get t square by 2. And for 1 to 2, we get y of t is equal to integral 0 to 1 tau d tau plus integral 1 to t 2 minus tau d tau. So when we integrate this and substitute the limits, we get minus t square by 2 plus 2t minus 1. And when t ranges from 2 to 3, we get y of t is equal to integral t minus 2 to 1 tau d tau plus integral 1 to 2 2 minus tau d tau. So when we integrate these terms and substitute the following limits, we get minus t square by 2 plus 2t minus 1. So if you see here, for both these values of t, that is from 1 to 2 and 2 to 3, we get the same expression minus t square by 2 plus 2t minus 1. Hence we can combine the limits of this t. Next, for t ranging from 3 to 4, we get y of t is equal to integral t minus 2 to 2 minus tau d tau. When we integrate and substitute the limits, we get t square by 2 minus 4t plus 8. Now using these values of y of t, if we plot the we get the signal y of t is 0 for t less than 0, t square by 2 for 0 to 1, minus t square by 2 plus 2t minus 1 from 1 to 3, t square by 2 minus 4t plus 8 for 3 to 4, and 0 for t greater than or equal to 4. So if we plot the signal for various values of t, we get this as the y of t.